Hi guys, welcome back to my lectures for programming in Go. This is the second part of topic 101, basic components of a Go program. In this part, we will learn about the basic types and operators in Go. So let's start with the basic types in Go. Here is the list of all basic types in Go. The first one is bool, which is for a boolean value, and string is also a basic type in Go. Go has 5 different basic types for integers. So except for int, the 4 other integer types are fixed length. The number after the word int indicates the length or the number of bits used for that data type. For example, int 8 means an integer type with 8 bits wide. And it has 6 different basic types for unsigned integers, including uint, uint8, uint 16, uint32, uint64, and uint.ptr. The uint.ptr is for pointer. So similarly, the uint8 or uint16, etc., are fixed type unsigned integer, and the number in the name of the type indicates the length or the number of bits used for that type. And the type indicated by the keyword byte, it is an alias for uint8 because a byte is the same as an unsigned integer of 8 bits. And rune is an alias for int32, okay, which represents a Unicode point. There are 2 basic types for floating point numbers in Go, including float 32 and float 64. And as you may guess, float 32 has 32 bits, and float 64 has 64 bits to represent the number. Go also has 2 different types to represent a complex number, including complex 64 and complex complex 128. Okay. Note that the uint and uint.ptr types are not a fixed length type. Okay, so they are usually 62 bits wide on a 62-bit system and 64 bits wide on a 64-bit system. In other words, the length of these 3 times depends on the system that the program is run on. And when you need an integer value, you should use the int type unless you have a specific reason to use a size or unsigned integer type. Here is an example Go program that uses 2 basic types, bool and complex 128. To use some functions with the complex numbers, this program imports the cmplx package, which has the import path mask /cmplx. Of course, it also uses the standard package fmt to use the printf function. Using a factor var statement, this program declares 2 variables at the package level. The first one is a bool variable named to be and initialized with the value false. The second variable is a variable z of type complex 128. The value of z is initialized to the square root of the complex number equal minus 5 plus 12i. Recall that a complex number is the sum of a real number and an imaginary number. An imaginary number is the product of a real number and the unit imaginary number I, whose square is minus 1. In Go, an imaginary number is written as a real number followed immediately by the unit imaginary number I. So there's nothing in between. Okay, so no asterisk or multiplication signs in between the real number and the unit imaginary number I when you form an imaginary number in Go. And you can use the printf function of package fmt with the %t formatting flag to show the type of the variable. Similarly, you can also use the %v formatting flag to show the value of the variable. So here, the first printf statement in the main function of this program shows the type and the value of variable to be. And the second printf statement here shows the type and the value of variable z. And here is what these two printf statement prints out. So it shows that the type of to be is bool and the value is false, and the type of z is complex 128 and the value is 2 plus 3i. When you declare a variable without providing an explicit initial value, then by default, the variable will be initialized with the 0 value of its type. The 0 value for a numeric type such as int or complex 128 is 0. The zero value for the bool or boolean type is false, and the 0 value for the string type is the empty string, which is written as a pair of double quotes with nothing in between. For example, in this program, we declare 4 variables I, F, B, and S without initialized values. And then we print out the values. Okay? This shows that variable I and F, which are of numeric types, int and float 64, received value 0. And variable B, which is of type bool, receive value false, and variable S, which is a string, has the empty string as its value. Like in other languages such as C and Java, you can convert the value of one type to another type in some cases. In Go, you can use the expression of the form t of v to convert the value v into the time t. For example, here you can declare a variable named I of time int and initialize it to the int value 42. Then the expression of float 64 of I will convert the int value of I to a value of time flow 64, which can then be assigned to a variable f of time flow 64. Note that unlike in C, in Go, the assignment between items of different times requires an explicit conversion, which is the one that use this form. Okay. So if you write f equal I in this example, you will get an error because f is of time flow 64 and I is of time int, so they don't match each other. Similarly, you cannot directly assign a value of time int such as such as variable I to a variable of time u int such as the variable u, even if the value of time int is an unsigned value. Okay? You cannot directly assign a value of time u int to a variable of time int either, although mathematically every unsigned integer is an integer, but in Go you cannot assign a value of one type to the variable of another type. Okay? So this case will also lead to an error. Also, unlike in the programming language C, in Go, arithmetic operations and comparison between values of mismatched times are not allowed. For example, the multiplication between x and y, where x is of type flow 32 and y is of time int, will result in an error. And the error message could be mismatched times int and float 32. Similarly, the comparison between x and y, where x and y are of different times, is not allowed. But mathematically, since both x and y are of numeric values, we should be able to compare them or apply an arithmetic operation between them. So in such a case, we need to use explicit conversion. For example, you can convert the value of x into int so that it has the same type as y before multiplying it with y. Similarly, we can convert the value of y into the same type of x, which is a float 32, before comparing it to x. When declaring a variable without specifying an explicit type, either by using the colon equals syntax or var equal expression syntax, then the type of the variable is inferred from the value on the right hand side. When the right hand side of the declaration is type, the new variable is of that same type. For example, suppose a variable I has been declared to be of type int. Then the short variable declaration j colon equal I will make variable j to be of type int as well. When the right hand side contains an untyped numeric constant, then the new variable may be an int or float 64 or complex 128, depending on the precision of the constants. Int is the default type of integer constants. So when the right hand side is a whole number, as in the statement var n equal 42, then the new variable n will get type int. Okay? And Float 64 is the default type of floating point constants, which are any numeric values written with the decimal point. So in this short variable declaration f colon equal 3.142, the variable f will get type float 64. When the numeric constant is written in the form of a complex number, that is with an imaginary number, then its default type is complex 128. So in this declaration of variable g, the variable g will have a type complex 128. Generally, the default type of untimed constant is determined by its syntax. An untimed constant can appear in an expression that involves arithmetic operations or comparison. In an operation between an untimed numeric constant and a timed numeric operand, then the untimed constant gets the same time as the timed operands. This is because Go doesn't allow operations that mix numeric types, as we have discussed before. And the result of an operation has the same time as its operands. For example, in the multiplication between 12 and variable x, where x has a type of float 32. The constant 12 has a type float 32 as well. So as a result, the type of the anti-operation of 12 multiplying x is float 32. But in the multiplication between 12 and variable n, which has a type int 16, the constant 12 has a type int 16. Okay? So how do we know that? That is because the type of the anti-operation of 12 multiplying n is int 16. So the type of each of its operands must be int 16 as well. Similarly, in the multiplication between 0.1 and variable x, the 0.1 constant has the same times as variable x, which is float 32. And so the multiplication result has a type of float 32. The same syntax rule is applied in the multiplication between 0.1 and the variable n, which has a type int 16. But since 0.1 value cannot be truncated to an integer value without losing some value, this leads to a syntax error, and this is the error message: untimed float constant truncated to int 16. But in an operation between two untimed numeric constants, such as 12 multiplied with 0.1, then both constants get the default type of the constant with higher precision. So for example, in the multiplication between 12 and 0.1, both constants 12 and 0.1 have type 64 because the constant 0.1 has higher precision than the constant 12, and the default type of 0.1 is float 64. So as you can see, the type of this multiplication is float 64. Go also has the same binary operators for arithmetic, logic, and comparison as in the language C and Java. But in addition to those common binary operators such as multiplication, division, modulo, addition, subtraction, comparisons, and or, Go also has bitwise operators, which will be explained in more details in the next slide. Here is the list of binary operators in Go, listed in the order of decreasing precedence. Those in the same line are of the same precedence, and those in the top line have higher precedence than those at a line below. Also, for each operator in the first two lines in this list, there is a corresponding shorthand shorthand assignment operator such as plus equal or multiplication equal or minus equal, etc. This is the description of the bitwise operators in Go. The operator denoted by the ampersand symbol is bitwise AND. The operator denoted by the vertical bar symbol is bitwise OR. The operator denoted by the caret symbol is bitwise XOR when used as a binary operator. But when it is used as a unary prefix operator, then it is bitwise negation. For example, when you write 9 caret 1, it means 9 XOR 1. The binary representation of 9 is 1001, whose only leftmost bit is different from the binary representation of 1. So 9 XOR 1 is 1000 in binary, which equals 8 in decimal. When writing caret 9 alone, it means applying the bitwise negation to number 9. And here the value 9 is of a time int, so its binary representation as a time int actually contains a number of bit zeros preceding the 1001, so that the total number of bits is either 32 or 64 depending on the system. So the bitwise negation of 9 is a series of bits 1 before the 0, 1, 1, 0. In the int type, a binary number with the leftmost bits 1 like this represents a negative number. And so when you apply the bitwise negation of u in 8 of 9, you will get a positive number, because in this case, so it works the same, except that so now you replace the 3 dot here with 2 0, and so then the result of bitwise negation of u int 8 of 9 could be equal to 1 0 1 1 1 1 0 1 1 0. So you just replace the 3 dots here with 2 bits 1, and that binary number is equal to 246 in decimal. The next bitwise operator is the combination of the bitwise AND and the bitwise negation, and it is denoted by the ampersand followed by the caret, and it is called the bit clear operator. For example, when you write 3-bit clear 9, you will get the same result as applying the bitwise negation of 9 and then apply the bitwise AND between 3 and the bitwise negation of 9. So in both cases, we get the same result. The last two bitwise operators are the left shift operator and the right shift operator. The left shift operator is denoted by double less than size, and the right shift operator is denoted by double larger than size. When you write 9 left shift 2, that means shifting all the bits in the binary representation of 9 2 bits to the left. This is equivalent to adding 2 0 bits at the end of 1001. So the result is 100100, which is equal to 36 in decimal. And when you write 9 right shift 1, that means shifting all the bits in the binary representation of 9 1 bit to the right. It's the same as cutting the last bit of 1001 off. So the result is 100, which is equal to 2 to the second or 4 in decimal. So the last topic in this lecture is named constants. In Go, the const keyword is a keyword introducing a name for a scalar value such as 2 or 3.14 or just or some string. Such values, named or otherwise, are called constants in Go. Okay? And so when we use the const keyword, we give it a name. And so name constants are declared like variables, but just use the const keyword. So here, these are the two named constants, pi and n, and they are declared at the package level. And so instead of using the var keyword, we use const. And constants can be character, string, boolean, or numeric values. But constants cannot be declared using the short declaration syntax or the colon equal syntax. And here is an example of how we declare constants. So in addition to the constant declared at the package level, you can also declare constant within a function, such as within this function main. So here we declare the constant named word to be of this string. Okay? And we declare the constant true to be of type bool because we assigned it to a bool value. Okay? And so here n is a constant of type int, and it has a value 15, and pi is an untyped constant, and its value is 1.14. Right, so many common constants are numeric constant, and numeric constants are high precision values. An untyped constant will take the type needed by its context. So an int can store at maximum a 64-bit integer or 32-bit integer, depends on the system, right? And in this example, we declare two numeric constants named big and small. And so here we use the factored count statement, just like the factored var statement. Okay? And so the constant big is defined to be equal to 1 left shift 100. So note that so 1 left shift 100 is equal to 2 to the 100, and small is equal to the value of big and right shift 900. So that means that we shift big right 99 places. So the small is equal to 1 left shift 1, which is equal to 2. And so now when you try to print out the value of big, you will see that it will cause an overflow into error, because this has, like, in order to represent the full values of this number, you will need 100 bits, but an integer can have maximally 64 bits. So this causes an overflow into error. Right? So you need to pay attention to when you use like the big number. All right, so that's the end of this lecture. Thank you for watching, and we'll hope to see you again in the next lecture.